Okay, so welcome everybody to the first of a series of webinars from the Alluvia project. The Alluvia project aims to realize Illumina waveguides, which are applicable across a wide region of the spectrum. And we have a series of webinars looking at potential use cases of these Illumina waveguides. And today the focus is on applications in trapped ion quantum computing. And it's a pleasure there to have with us Philip Holtz from AQT, and Alex Cesar and Sofia Canacastro from Infineon, who will tell us about their application case and the things that they look for in this platform. But first, let me pass over to Sonia Garcia Blanco, who is the lead on the project and is the developer of the technology. And she's going to tell you a little bit about the Alluvia-driven Illumina platform. So Sonia, over to you.
Yes, thank you very much, Jonathan, for the very nice introduction. And I'm trying to put my presentation set up, and everything is going okay. So first of all, I would like to introduce you, as Jonathan said, the EIC transition project Alluvia, which stands for Aluminum Oxide Integrated Photonic Platform for Applications in the Ultraviolet. And this is the overview of the project. So the goal of the Alluvia project is to establish the first worldwide aluminum oxide commercial integrated photonic platform to enable new markets in the ultraviolet wavelength region. So this is the things, the activities that we're going to do in the project. We have a big work package on technology maturation, where we're going to ensure that the technology gets reproducible, and that we develop a library of building blocks that then can be utilized for different applications. And there, with our partner Fix, we also develop the packaging that is necessary for these applications. And we are going to validate the technology in the project with two main applications, UV Raman spectroscopy and ion trap quantum computing, which is the topic of today's webinar. And of course, we want to commercialize the technology, and for that, we have already done the spin-off Alluvia Photonics, which is the vehicle by which we are commercializing the technology. So why aluminum oxide? Probably you already have heard about the platform, but I would like to remind you that it has a very wide transparency window, extending all the way down to around 170 nanometers. That's the bandgap of the material. And all the way to the mid-infrared, around 3 micrometers. It has very low propagation losses, and here are the losses from the 369 up to the near-infrared 1550. So we can see that at 369 we have 1 to 2 dB per centimeter, and in the near-infrared 1550, 1 to 5 dB per meter. Okay, not to pass the slide, I need to just go through the next one. Okay, do you see my next slide? Yes.
Yes.
So another important property of the aluminum oxide is that it has a very high rare earth ion solubility. So that means that you can dope it with different rare earth ions, such as erbium, thulium, neodymium, to get amplification in different wavelength ranges. And we have advanced also a lot in this development, and now we can produce more than 20 centimeter long spirals with net fiber to fiber gain and quantum limited noise figure. Okay, my computer is going very slow. Let me just change the slide. During the Alluvia project, we have managed to ensure that we have very high lithography fidelity. That means that what we write in the mask is what appears in the wafer. And you can see here, design 130 nanometer line that became at 130 nanometers line, 600 nanometer line that became 600 nanometer line, and a gap of 100 nanometers that was 100 nanometers. We can also do gratings. So here is an example of a grating with 193 nanometers gaps that actually made it to the wafer with, you cannot see it, but it's very small, but it's actually between 193 and 194 nanometers. So it's like almost perfect. And these gratings were used by the ETH group of Jonathan to produce back-focusing visible UV vortices. And these are the gratings that we produce, and this is the image that I took from these gratings. We have also done in the first iterations some UV power splitters, because we didn't have them in the lab, so it's very interesting to have them. So basically, just a 50-50 splitter that then was packaged by our partner in packaging Fix. If you want to try the technology, of course, we can also offer it commercially to external partners via the MPW grants. We are just now closing the MPW4, but there will be two more still this year, one at the end of September and one in December. So you can just check in our page and contact us if you have any questions. So thank you very much for your attention. And sorry for the technical problems.
Thanks very much, Sonia. We have 1 minute or so for quick questions. Are there any questions to Sonia at that point? I look for hands and things. I don't know if I see where they would come, but okay, I don't see any at the moment. So I would say let's move on to our next, which is a guest speaker to our project, which is Philip Holtz from Alpine Quantum Technologies. Alpine Quantum Technologies work on trapped ion quantum computer implementations, and I think they both sell access and systems to people. So Philip, do you want to share your screen?
All right.
Great.
Okay. Yeah. So thanks, Jonathan, for the kind of introduction. So today I'd like to talk about photonic integration in scalable trapped ion quantum processors. That's a vast topic in a way. So in the 20 minutes that I have, I think I'm just going to manage a brief analysis of requirements of the involved technologies. But I'd like to start actually with presenting a little bit what our company AQT is actually doing, who we are, just for all those that are not maybe familiar with us. This will be the first couple of minutes, and then I switch gears and give a brief introduction into trapped ion quantum computing. This is really very brief in a nutshell, just to get everyone on board, that we are on the same page, to then dive into the main topic of my talk, which will be the technical requirements that we're facing when trying to integrate optics with ion traps. Okay, so just very briefly about our company. AQT is a medium-sized company in Innsbruck, Austria, that's building quantum computers. So we have trapped ion quantum computers, more precisely, with currently around 20 ion qubits. We've demonstrated 24-qubit entanglement. Our machines have currently a quantum volume, which is one of the key metrics measuring the performance of a quantum computer. So we have a quantum volume currently of about 128, not about, exactly that. So that's equivalent to 7 qubits. And the quantum memory or coherence, if you wish, in our systems is equivalent to about 1,000 gates. A key aspect of our systems is that they are rack mounted. So what you see here on the right-hand side, these two cupboards, in a way, these are 19-inch racks with a footprint of 1 square meter and about 1 meter height, and that's everything we need. So in there is really all the equipment for a trapped ion quantum computer. They're cloud accessible, they're compatible with data centers, and very energy efficient. So if you run them, it only takes about 2 kilowatts of power. That's the same amount roughly that it takes if you make yourself a cup of tea. And with these machines, we've demonstrated various use cases, chemistry-wise or also process optimization-wise, like you might in the industry. And if you're interested more in that, I recommend to have a look at our webpage. Just at a glance, our company, I said we're medium-sized. We have 29 employees at the moment. We started off with around 15 million euros investment, have grown ever since then. Since 2021, we actually managed to generate revenue in the 7-digit euro range with about 200% of compound annual growth rate since 2019. AQT has a tiered product strategy. That means we have 3 different branches on how we generate revenue. We first sell standalone quantum instruments. That's what you see on the left-hand side. This can be an ion trap. It can be an ion trap in a vacuum assembly. It can be other accessories like laser accessories or electronics. That's the first tier. Then we give cloud access or offer cloud access to our own quantum computers, and we sell the entire quantum computers like you see on the right-hand side. From a technical expertise point of view, AQT has expertise in, of course, ion trap technology. So the knowledge of how to make state-of-the-art ion traps, how to put them under vacuum, how to operate the lasers and with the right specifications. Everything basically that's related on how to get a trapped ion quantum computer to run. And then we integrate all these different ingredients from the vacuum to the lasers and so on and so forth. We add environment control like thermal control, electromagnetic interference to just get the entire environment correct. And we're aiming here at robust and maintainable solutions. And to run the quantum computers, we also have our own full stack software. So we do the RF pulse control to control the laser pulses hitting the ions, task scheduling, compilation of quantum circuits to the native gates on our machines. And as I said, the remote and cloud access. AQT is also very active in the worldwide research ecosystem. It's mostly EU. So for instance, just to point out two projects that we are working in that are hardware related. That's on the left top, the EU flagship project Millennium, and then the left bottom, the KIA project, the Quantum Internet Alliance. So as I said, the core competence of AQT is to have trapped ion quantum computers in rack systems, in standardized 19-inch racks. That's what you see on the very right. And then if you open the door, you look in, then you see the thing in the middle, that's the vacuum chamber. So trapped ion quantum computers need to be operated under ultra-high vacuum. And then around this vacuum chamber, there are all the optical elements, the electronics elements assembled. And at the center of the vacuum system is the ion trap. That's what you see on the left-hand side. That's AQT's Pine Trap quantum processor. Right, now from this brief introduction, I'd like to switch gears and explain in a nutshell how a trapped ion quantum computer actually works. The basic ingredients that we need are two. We need qubits, which in our case are ions. And then we need to put them into a harmonic oscillator, and that's the trap. So the qubit is basically just a two-level quantum mechanical system with the two states 0 and 1. And the trap is basically acting as a harmonic oscillator confining potential. What we can do now with lasers or also microwave radiation is manipulate the quantum states. So we can switch the qubit states, we can put them in superposition. We can also manipulate the motional states, so the state of this ion particle in the ion trap. And then using the fact that when we put multiple ions in the same trap, they actually have a shared motion. Now we can also create entanglement between them. And entanglement is, I would say, the core or the key ingredient that we need for a quantum computer. So this is conceptually what you need. If you'd like to implement that, it looks maybe like that. It's still very conceptual, but roughly. The ion qubits, well, here we have a variety of different atomic species that we could work with. Here we have, on the left-hand side, you see the example for calcium-40 ions. You see that it's not just two transitions, but a whole bunch of them. We can use them for different purposes. So in blue would be transitions that we can use for Doppler cooling of the ion motion in the trap. And then in red at 729 nanometers, the S to D transition, that would be the qubit transition. And then we have a qubit quench transition at 854 nanometers. So these would be the qubits, and then we put them in their harmonic oscillator potential that's being produced by the ion trap. And here we see an example, macroscopic Powell trap on the top right. In these traps, you use electric potentials, electric fields, static fields, and also AC fields in the RF domain. So we call them RF potentials. And these generate the confining potential for an ion crystal in ultra-high vacuum environment. And often this is even a cryogenic environment. Then we use lasers to pointing at the individual ions to drive the atomic transitions. We have a camera on top to detect the fluorescence by the ions, and in this way measure in which quantum state they are. And of course, this is very simplistic. we can use now sophisticated microfabrication technologies to make much more complex traps, like you see at the bottom. This would be an example of a linear surface trap. So here, again, you have RF electrodes in green, you have DC electrodes in blue, and they are all now on a microchip. And ions, the red spheres, would be levitated at some distance d from the surface. Okay, now with this, I come to the main part of the talk. If we now want to scale the trapped ion quantum processor, and by scaling, I mean here increase the number of qubits to hundreds, eventually thousands, some people say maybe millions of ion qubits, while maintaining the amount of control that we have. That's what I mean by scaling. And actually that means even improving on gate fidelities that we have right now, because otherwise just increasing the number of qubits doesn't help. So if we want to do that, then we have to push forward in different technological areas that I've marked here in these different colors. So there may be a few more, but I think these are the most important ones. First, we need to build the traps themselves, microfabricated traps. This can be surface traps, like I've just shown you. We can also make 3D traps using microfabrication technologies. They have some advantages and also some disadvantages. There's also something in between, like 2.5D traps, where maybe you have a three-dimensional arrangement of electrodes still, but the RF is only on one side, which has some technical advantages. So that would be the trap side. Then to bring all the electric, all the electric signals onto the trap, we need a scalable voltage supply system. So this would be DC voltages. Something that people have already done in the past is just directly integrate digital to analog converters, DACs, with ion trap chips, or just put them at least in vacuum. We most likely need electrical multiplexing capabilities. That's something several people are looking into at the moment. We also need to think about the integrated detection. So how do we collect the fluorescence? People have in the past already put photodiodes, like 10 years ago, underneath ion traps, but more recently they started to integrate superconducting nanowires or single photon avalanche detectors with ion traps. And then, of course, we have, that's probably the core topic here, integrated light delivery at the bottom left. So what people have done so far is integrate with ion traps waveguides and grating couplers. Some people also use lens arrays instead. Optical multiplexing, that's something that I think will be needed. Frequency amplitude control, all of these things we'll cover in a bit more detail in the next slides. So this is just to tell you that there are many different technologies that we need to drive forward. We need to ensure compatibility between them. And in the next few minutes, I look a bit more in detail on the microfabrication of traps and integration of light delivery aspects, which I think are the aspects that the Alluvia consortium is also looking into. Okay, so the microfabrication of ion traps. So I would say roughly we can say from the requirements point of view, we can divide this into mechanical, electrical, material related and thermal requirements. And just to give you some idea of how such a device looks like, I show a very nice example here on the right-hand side. That's continuum's racetrack trap. So I would say that's one of the most advanced traps out there at the moment. And of course, also like the device where there's the world record on performance at the moment. So in general now, for trapped ion quantum processors, from a mechanical point of view, most of these chip traps have a size of roughly maybe a centimeter. And when we look at the resolution that we need to make the electrodes, that's on the order of a micrometer. And here the resolution and the precision to make them has to be kept over the entire size of the electrode assembly. And one thing that we always have to keep in mind, we always need optical access. Of course, the goal is to integrate light, but then the detection maybe is not yet integrated, or you have only integrated some of the wavelengths that you need. So optical access, that's something you always have to think about. Then the next point would be electrical requirements. To operate the traps, we need electric signals. Here, the materials that we employ, or the technology, needs to enable a high voltage strength. So for the RF signals that are around 10 to 100 megahertz maybe. We need 50 to 500 volts. This very much depends on the trap design. These are just rough numbers, but that's the ballpark. And for the static voltages, it's maybe a factor of 10 less. We need to ensure low capacity of the entire device when we drive DRF, a low impedance for the routing to the individual electrodes, and it's essential to have more than a single metal layer. We need multi-metal layers to be able to connect electrodes in a complex electrode design. From a material point of view, we need high conductivity electrodes, so good metals basically as a choice for the electrodes. We need to ensure low RF loss. That's something important in the choice of substrate. So silicon, for instance, is something that can be tricky if you don't do proper shielding, at least. Dielectrics, it's something that ions typically really don't like. You don't want to expose them to dielectrics. You have to shield everything with metal. And everything has to be UHV compatible, because in the end, the ion trap is operated under ultra-high vacuum conditions. From a thermal point of view, we need high thermal conductivity to get the heat away from the trap chip. Often, this is operated in a cryogenic system, so we have limited cooling power, and overall, everything has to be cryogenically compatible. So I mentioned this in so much detail because one of the standard ways of integrating light with ion traps is to basically put the electrode stack on top, put the electrodes directly on top. And then that's all something you have to take into consideration. Now coming to the integrated light delivery requirements, let's again have a look at a very nice example that's here on the left-hand side, Sandia's multi-site addressing chip, where we see a surface trap and then these tiny little balls above. This should be the ions. And now you have addressing of these ions with light coming from structures in the plane of the trap chip. So from a very general point of view, we always will need more than one wavelength. Typically, we need 4 or even more wavelengths in the range of 350 to 700 nanometers. So that's actually quite well matching to aluminum oxide, as we've heard from Sonia before. The exact value depends on which ion species you want to pick. Then if we look on the left-hand side for a single processing zone where we use light to manipulate ions, in this example, you already need 4 different optical channels. So if you scale this up, you easily get to tens and hundreds of individual optical channels that you need to realize. For some of the light, we don't have a large desire for or need for power. So Doppler cooling needs not a lot of power, but other things like the quadrupole transition, the qubit transition needs something like a few milliwatts per optical channel. The entire optical supply system needs to be low loss. So here we talk about a few percent level, and this has to be long-term stable. So in particular in the UV, bleaching may be really a problem. We always have to have everything single mode and polarization maintaining. As I said, the silicon, that's something we need to shield because the ion trap operation doesn't like it typically. It has to be cryogenically and UHV compatible. And something I think that maybe sometimes gets overlooked, when we scale this up, also stray lights and beam dumping, a management of these is something that will be essential. So we don't want unwanted excitation of ions that we don't want to excite. We don't, so that would be something we call crosstalk. We also, when we have detectors around, don't want to increase the dark count just by some stray photons flying around. Also, the surfaces of the ion trap shouldn't be charged. So we need to come up with concepts here. Also, dumping lots of optical power directly into a cryogenic system is typically not a good idea. Then we can break it down roughly into what kind of elements would we need in such an integrated optics scenario. Of course, waveguides to route the light on chip. Something that's important here is small bending radii. So if you look at this example on the left-hand side, individual processing zones may be at the distance of a couple hundred microns. So we really need to bend the light on the optics chip below on a similar length scale or preferably smaller, just to not have an excess in footprint. Of course, we need to get the light into the waveguides. We need in-coupling interfaces to fibers. We need to get it out somehow and shine it on the ions. That requires out-coupling interfaces, suitable beam shaping, for instance, using grating couplers. We need beam splitters, maybe combiners. Then if you think about scaling this up even more, well, at some point you will face the problem that waveguides need to cross. So that's something we need to think of. We need to show building blocks also at the wavelengths that are relevant for ions. Maybe mode converters are of interest. We've already seen an example of a vortex beam before. Polarization control, and I guess the list can be extended even more. The last thing would be active elements. So optical multiplexing, we just in the end, we face a routing problem. If we need to bring everything into the vacuum system from outside, that's challenging. So optical multiplex to get from one channel to n, maybe 2 to n even, if we think about entangling ions. Amplitude control, switch individual channels. Typical gate times are on the order of microseconds, so that would be a relevant time scale here. And when the channel is off, it really should be off. So depending on, of course, which wavelength it is, we need to suppress it greatly. Maybe frequency control, that's something you can argue you can do from outside. Of course, everything you can have inside can be interesting. We will find applications, just maybe it's very challenging. Polarization conversion. Okay, now I think I'm almost over time, so it's the last slide. I just wanted to convey to you some idea of what it means to scale a trapped ion quantum processor. I pointed out 4 different areas of technology that we need to push forward. I focused a bit on what I think is relevant for the Alluvia consortium. And I want to say that these are not independent technologies. We always have to think of everything together, because one leads to requirements on the other. So for instance, when we have detectors there, we really have to think about the stray light. And when there's the silicon, well, how does it affect the ions or the RF drive? So that's an integration challenge. I think it requires fundamental research and more technological development efforts. But if I may just end with a personal note, just working in this field, I think it's a highly interesting challenge, integration challenge, and I think it's actually lots of fun. And with that, I thank you for your attention.
Great. Thanks very much, Philip. Oh, wow. I see clapping springing up off the bottom of my screen. Do we have questions? How would people ask questions? So I guess maybe I start off with questions. If you were to point at some particular element that you would want from Sonia today, what would you think would be the most important thing that you would like on your wish list?
Okay, so maybe I quickly bring the wish list up again. I see now it also found the slides. Yeah, so I think the active elements, that's really cool, but I think it's further away. Let's look at the passive elements for now. So waveguides, we've seen work well in the red. In the blue, it's a problem. I think looking at just simply showing the waveguides and showing low loss across the entire chain. So how do you couple in with low loss? How do you, okay, transmission is probably more or less easy, but then I think a problem is how do you ensure small bending radii and still efficient grating couplers? I don't know. So to me, it seems like this. Maybe these are conflicting requirements, and probably need some technological way of figuring this out. So that would be something nice to see, I think.
Yeah, great. Thank you. Any other questions? Please shout out if you have a question, because somehow I don't see where your hand would pop up. So, and maybe another one then from my side. Then in these 3D macroscopic traps, do you see a role for integrated optics there? And how would you, or how are you thinking towards integrated optics?
Not so much. So in the macroscopic trap, like the really traditionally machined ones, no, not. But if we think about the SLE traps that you've also at ETH pioneered, yes, I see potential there. I think you can make the structures in a way that they become compatible. Now, of course, this would not be monolithic integration. This would mean that you have the trap separate, I guess, from the optics chip. But I see that this would be something really interesting.
Great. So with that, then let's thank Philip again for the nice talk and also for answering some questions. So our next speakers are from Infineon, and I think it's split into two parts. I don't know how you guys are going to handle it, but the first speaker, I think, is Sofia Cano Castro from Infineon.
So, yeah, actually, I will begin.
Oh, okay.
Well, we'll transition over to Sophia.
Okay. Yeah.
And you will see in the outline how we try to, or how we plan to share the talk. Perfect. Yeah, thank you. And today, Sophia and me, we would like to guide you through our presentation that talks about photonics in our ion traps that we fabricated in Infineon Technologies. And we would like to separate our talk into an introductory part that I'm going to guide you through. So here we talk about ion trap chips and how we make them at Infineon, and also what we do at the ion trap systems group at Infineon Technologies. And in the second part, Sophia will go into the details of the photonics part that we would like to integrate in the ion trap chips made by Infineon. So I would like to complement the talk by Philip by asking why are we trapping ions? And ions are at the core of two emerging technologies. The first one being optical atomic clocks, which are a very precise time standard, even better or much better by roughly 3 orders of magnitude than standard cesium clocks. And just for you to get a feeling how accurate they are, so an optical atomic clock can measure a height difference in the gravitational field due to the redshift on the order of 1 centimeter. So that's, I think, pretty impressive. And the second application of ions or trapped ions are trapped ion quantum computing. And with quantum computing, I probably don't need to tell you that you know that quantum computers can solve special problems. And one of those special problems being natural, for quantum computer, natural problem, this is quantum simulation. And how does that work? So ions have electronic energy levels that can be driven by laser pulses, but also by microwave radiation. And with that, we can do quantum computation and we can drive clock transitions. And we can only do that when we are able to confine single ions in space. And for that, we use ion traps. So here I would like to explain how ion traps work. You already know from Philip, so I will go over that rather quickly. So the upper left image shows a turntable that is trapping a ping pong ball, and it is an analogy for how we trap ions. Ions are trapped by rotating or changing electromagnetic fields that come or are generated by so-called RF electrodes on top of our ion trap chips. So on the right image, you see one of the concepts how we could realize a large-scale ion trap chip. Here, the electrodes look like tiles of different shades of gray. And the ions here in this architecture are, they can travel along lines here that look like the streets of Manhattan. So we also have electrodes on top in the light gray where we can vary the voltage more slowly than with the RF voltage. So there are two kinds of voltage, and with this slow voltage, we can move those ions along those streets, which is an important, let's say, function of ion traps to enable large-scale quantum computation. For clocks, this is a bit different. All right, so what do we do at Villach? In Villach, we have a high-volume production site, but also we fabricate ion traps in collaboration with other Infineon production sites in Regensburg, Dresden, and also Kulim. But in Villach, we do most of the work, and also our ion trap system team is located in Villach. Actually, if you see my mouse pointer, it's in this building here, the small one. So in Villach, we have 5,000 employees, and here we make or produce 2,000 different products, which requires a very flexible fabrication line, and this can be leveraged for our ion trap fabrication. So the wafer diameters that are being processed here in the fab is range from 150 millimeters to 300 millimeters, and here I have to say 150 is going to be phased out soon, and we focus on 200 millimeter wafers. The substrates used in this fab are also very diverse. So we have silicon, of course, but also gallium nitride on silicon, silicon carbide, glass, and sapphire. And the underlying substrate are those that we use in the ion trap systems group. I also want to stress here that we have certain requirements for material zones, so contamination with dopants, especially in certain parts of the fabrication line that deals with the core part of the transistor, which is also an important factor to take into consideration when we collaborate with other fabrication sites. And of course, we need to maintain a low particle number on the wafers, which is also of concern when we send wafers to another location, just for you, for your information. And on the next slide, I would like to argue why industrial microfabrication is beneficial for ion traps. So future ion traps will require complex stacks of metal, different metal stacks, photonic layers, vertical interconnects, and integrated electronics. And here we can really leverage the advantages of industrial microfabrication that provides stable and repeatable processing, high automation that also provides metrology and inspection on a very short time basis. And due to the high automation, we also have a very low defect count. And on the left image, here we shown a defect scan of a photonic layer that we made at Infineon on a 200 millimeter wafer. And we see here we have only 30 defects with a size larger than 100 nanometers on this wafer, which I think is pretty impressive. This is really low. Yeah. All right. So what do we do at the Ion Trap Systems Group? Of course, our focus is on trap fabrication. So we develop all the processes that are needed to produce an ion trap, but we also go beyond that. We look at the quality of our layers, especially the metals that are on top of the ion trap, because those metals they might influence the ion due to their to the fields, the static fields that are present due to the metal. I will show you later what I mean with that. Of course, we also integrate or would like to integrate optics, photonic layers, not just photonic layers, but also avalanche photodiodes, which are developed at Infineon for cryogenic temperatures. Another pillar, very important, this is also our strong suit at Infineon, is electronics integration. Here we design multiplexers and DACs for ion trap applications that also work at cryogenic temperatures. And lastly, we also investigate different trap types like panning trap on chip. We look into Rydberg ions and also investigate novel kinds of shuttling. Before I told you that we can vary the slow voltages for the ions to walk along the streets of Manhattan, but there's also another way where we can shuttle ions in 90 degrees to this slow voltage shuttling direction. And now here I want to illustrate what I just told you with 4 examples. So on the very upper left, you see 200 millimeter fused silica wafers where we fabricate ion traps on. On the upper right, you see a KBFM, Kelvin force microscopy image where we image the electrostatic potential that arises due to the metal. And here we investigate the influence of this electrical potential on the ion. Also, we make photonic layers, as we will see later, as you can see in this electron microscope image of this grating here. And on the lower right, you see an ion trap placed on top of a multiplexer chip, and they are connected with wire bonds. So, of course, we also want to deliver reliable ion traps, so we need to test them. Therefore, we have a testing lab at Infineon Villach, where we can actually run ion traps and trap ions, characterize ion traps before delivery. Also want to state, Infineon is not a manufacturer for quantum computers, but rather we would like to provide the hardware core. So that is the ion trap and some control hardware closely associated to that. And we rely on partners to provide other hardware and software. We have quite a, I would say, a good collaboration network in Europe where we collaborate with universities, but also with companies like Oxford Ionics and Electron. Well, here I would like to show our team at the Ion Trap Systems group. Roughly half of the team are experts who already have quite some experience in the field, and roughly the other half consists of students, mainly PhD students, but also master students that work on different exploratory different topics, the exploratory topics. And now I would like to give over the microphone to Sophia, and she will introduce to you the photonics details.
Sorry, okay. So thank you, Alex, for introducing most of our work with ion traps. And now I want to go on and go more in detail about the integration for the traps and our approach for this. So now if we go to the next slide. Okay, it's taking a while. Sorry about that. So I would like to first motivate why we are going for this integration approach, and what you see on the left side of the slide is what has been mostly demonstrated for let's say the laser control of ion traps, as it has already been explained. We rely on laser beams to address the ions and control the different operations we want to do on the ion. And the approach so mostly demonstrated so far uses phase-space optics to deliver the different wavelengths we require. And as you can see on the lower part, when ions scale up, so when we have bigger numbers of ions, this doesn't work as well. And we need to look for alternatives that can allow us to deliver hundreds of trapping sites, to deliver the laser beam to hundreds of trapping sites among thousands of ions that are moving around the trap, and to do individual addressing. And that is what you see on the right side of the slide, where we have some grating out couplers that are delivering each wavelength required to the different ions. And this not only works for scalability, but it also leads to performance gains, because now we reduce the vibrations and drifts that come from the first setup, which lead to errors in qubit operations. And we also, let's say, avoid beam pointing errors. So in general, it's also a gain in performance. And for this reason, we try to go to the second approach. And I think about the requirements for this approach, Philip already gave some insights, but what we would like to call the solution, or so what we need to, so the basic building blocks that we need to make this true, are to be able to couple light into a chip, to route the chip to the different ion sites, and to outcouple tightly a beam at the ion position. And these are the basic functionalities we want to fulfill in the near term. And here we have, let's say, an illustration of how that would look in an ion trap. So we would have different photonic layers addressing the ion. As you saw, so from the first picture, this is a cross section of our trap concept. And here we have two examples of groups that have shown this optical integration. So one is Jonathan's group with collaboration with PSI, where they presented this year a 20 trapping zone chip. And we also have examples from Sandia National Laboratories, where they did this for different species. And we translate this into the requirements for the photonic platform. And we see that this previous illustration gets much more complex when you start thinking about fabrication. So the electrodes now become multi-layer, so multi-metal layer for the electrodes. Then we also have the photonic platform that is non-ideal and has aspects such as roughness. And then we also have the fact that the layers beneath the photonic platform are still like under development. So we have now different requirements, and we summarize that into four main aspects we would like to share today, which are so the broadband functionality. As you can see, we have, at least for instance, if we address the calcium ion transitions that you can see on the right part of the slide, we have wavelengths on the 397 nanometer range and on the 729 nanometer wavelength. So this already sets the need for a broadband operation. Then we also want to tackle integration flexibility, so that we look into materials that are compatible to integrate with different stacks, substrates, and mostly that have a low temperature budget, so that we can look into multi-metal layers, for instance, below the photonic platform. Then about the most, let's say, non-ideal part of the photonic platform, we will start to see losses, and we will have challenges in the fabrication itself, because we need high confinement and low pitch to be able to deliver the let's say, tightly focused and carefully aligned beam we aim for. And as it was already mentioned, when you think of scaling into higher and higher numbers of ions, both the topic of packaging and modulating becomes relevant. And these are so the main things we want to keep in mind today. And with this purpose, we started the development of a photonic, so of some photonic platform at Infineon. And this is the first chip that was fabricated in our fab with a silicon nitride platform. And we see here some different characterization structures that we use for some first tests. And we optimized three different aspects of the platform development that we would like to share today. And the first one has to do with the quality of the thin films we require for this application. Since, as we mentioned, we need to stay in a low loss regime, and that requires low roughness layers that don't lead to scattering losses. Scattering losses would also lead to stray light and contribute to the problems that Philip already mentioned. So what we see on the first column is an atomic force microscope image that we took of a low temperature deposition layer, and then we compare it to the second picture, which is a fine polish of this low temperature layer. I hope you can see my cursor. And this is one of the things we first considered to improve the quality of our films. And then on the lower part, we see the comparison between ellipsometry measurements on silicon nitride and aluminum oxide. Because of this broad transparency window, we need materials that have that work and don't present absorption into lower wavelengths. And we see that silicon nitride might not fit all the way to, for instance, 397 nanometers. So these are ellipsometry measurements of our in-house films that we used for reference. And then on the second column, we have some examples of structures we fabricated, where we characterize the process the process development for creating out couplers, and also waveguide structures, where we measured the roughness mainly. And this was because, again, scattering is going to be induced wherever we see roughness, and so roughness in sidewalls is always a big problem for photonic structures. And here we measured around 1 nanometer roughness for our waveguides. And finally, we have built a characterization setup for these structures, where we would like to highlight one of the things we were interested in measuring, and was the polarization dependence of our waveguides. So we characterize a high confinement waveguide, so platform, and here we see the insertion loss for different lengths. And this is to obtain the propagation losses which came out to be indeed different for a T and a TM mode. And this is something we need to further investigate so that eventually we can have the control that was mentioned is required for ion trap working. And yeah, to these, so with this slide, we come to our conclusion and outlook. And what we see next for the ion trap, photonic ion trap development is to keep working on low loss platforms with a broader transparency window, to start thinking about photonic packaging solutions and on-chip modulation up to the megahertz regime, and to collaborate for further integration capabilities. So that is also why we're here today. And to summarize, we presented why how trapped ions are one of the leading platforms for quantum computing and atomic clocks, and how Infineon will be providing the core of these computers. So we want to make quantum processing units, and how photonics is necessary for scaling these QPUs, and development of the platform is key to be able to achieve this development. So thank you very much. We have now come to the end of our presentation, and we hope you enjoyed it.
Thank you very much, Sophia and Alex. Good. Do we have any questions for Sophia and Alex? I have one, so I will go ahead. Yeah. So you mentioned different substrates, and it's interesting to think, I mean, one of the challenges that I guess Philip pointed out was that silicon somehow has problems with charging and things that we're always worrying about. So how flexible is it in your case to be able to fabricate the different types of waveguides and electrodes on these different substrates, or are you constrained in some way to combine certain sets of technologies? You need to unmute, Alex.
Yeah. Thanks for an excellent question. Of course, that's pretty hard to switch substrates in a semiconductor fab that's so optimized for silicon. We are working on that heavily, let's say, because academic partners would prefer fused silica and sapphire, and also companies would prefer it if it was easy for us to integrate everything there, but it's not easy. However, we are working on that, and we still have to explore, especially for photonic layers, how the different substrates influence the fabrication there. Maybe to give you an impression why this is difficult, those substrates have different thermal or heat transport capabilities. During the process, this can influence already the position of layers, for example, but also they have different thermal expansion coefficients, and also that influences the handling in tools. So there's the small details that really matter here.
Yeah, thanks very much. Yeah.
Can I ask a follow-up question, maybe?
Yes, please.
And yeah, I pointed this out myself, that of course, like silicon can be, and also Jonathan said it again, can be troublesome. But then when you say on-chip modulation capabilities, for instance, I mean, there are of course big advantages of using silicon again together with the optics, because you can then tap into like all the different semiconductor elements that are already out there. So how do you see this? And is it really your goal to switch the substrates, or is this just one possible way, or is it still like due to other reasons silicon a better material, and then you need to adapt the shielding, or I don't know?
You want to answer that, Sophia? Or like I could start, and you can come in if you have more to say. So I think it is not our goal to switch from silicon to the other substrate as fast as possible. We will continue our development on silicon. Certainly, due to these obvious reasons that silicon is just a more established platform, if you think of modulation, of course, you might think of layers that can do that. For example, lithium niobate, that is probably not easily available on glass and on sapphire. So there are, of course, huge drawbacks of using those dielectric materials. But not all applications and not all ion traps we make right now require photonics or even modulation. And also, I want to add, there are ways to engineer around the problems of silicon. So in the end, we don't know which of those substrates might be the one we would concentrate on. So right now it's not possible to decide that. Do you have anything to add? No. Okay.
Thank you. I guess maybe one last question. I saw on your slides that you chose, I mean, silicon nitride has been traditionally used, but then you chose aluminum nitride. And of course, now also Sonia has this aspect of alumina. So can you provide some of the sort of advantages and disadvantages, for instance, of aluminum nitride versus how you see the other materials, or a comparison of the materials? You need to unmute, I think, Sophia. No, I can't hear you. Yeah.
Okay, then
Yep.
I will speak from here. Sure. So silicon nitride is, let's say, more mature technology from both from the photonic point of view, but also has been integrated in fabs for other applications. So it's the most readily available, and that is of course an advantage. There is experience with the structuring and in general application. But as we could see from the lipsometry measurements, for instance, the transparency window is not expanding into the, let's say, UV wavelengths as, for example, aluminum oxide and aluminum nitride do. And there is the huge advantage. I believe these materials still need more development just because they have been studied less. And again, there is a huge work to do in terms of roughness, for instance, to make them, let's say, as mature as silicon nitride. But if we talk mostly about aluminum oxide and aluminum nitride, I think there is the interest on aluminum nitride. It's also because of the let's say the potential capability of modulation, because here we have a piezoelectric effect that could be profited for perhaps, yeah, new applications, active applications in the visible.
Great. Thanks very much. So with that, then I'd like to thank our speakers. I'd like to advertise that there is a future upcoming webinar in this series, which will be on the 11th of July, again focused on the Alluvia project and its possible technological applications, this time with respect to sensing for biological and other applications. So with that, then I'd like to thank you for attending this webinar today. I would like to thank our speakers, Alex Cesar, Sofia Cano Castro, and Philip Holtz for their contributions, and I wish you